I'm going to pull up the course guide. This is from UVLE. So, okay, so we have an UVLE portal for EEE 131, and that is EEE 131 first sem academic year 2022-2023. If you are enrolled, no, then you should have automatically been included in this UVLE page. Okay. I already included both my THW and THX sections in this UVLE page. So this is going to be our venue for publishing all of the course material. Okay, let me pull up the course guide. Sorry. Sorry about that. Let me pull up the course guide. No. Okay, so this is the title of the course. It is electronic devices and circuits. Okay. So if you take a look at the course description, what are we going to take up here? You're going to take up the basic electronic devices. So what are these? These are diodes and transistors, and there are two types of transistors which we're going to take up: the bipolar junction transistor and the field effect transistor. And we're going to take a look at the typical applications of these devices. And then you're also going to learn how to analyze circuits which contain these devices. So in EEE 123, the prerequisite to this course, you learn to analyze circuits with the basic passive elements: resistors, capacitors, and inductors. So now we're going to bring it up a notch higher. You're going to learn to analyze circuits which include these basic electronic devices, diodes and transistors. So the prerequisite to this course is 123 and also Physics 72. Okay, the mode of delivery. There are going to be two modes of delivery of this course this semester. For all of the other sections except my section, it's going to be purely synchronous consultations and asynchronous lectures. But for my section, we decided to make available to you face-to-face lectures. So the THW and THX classes are going to have face-to-face lectures. But that's not going to happen right away, because there are guidelines that have been established by the university for face-to-face lectures. And we have to make sure that the way we conduct the sessions will be in accordance with these guidelines. So expect the face-to-face lectures to happen. I doubt whether it will happen late September. I think more probably face-to-face lectures will start early October. Okay, why did we decide to have face-to-face lectures? We decided to have face-to-face lectures because our experience over the past 2 years during the pandemic is the very poor absorption of students of the subject matter when they rely purely on asynchronous material. In fact, it is quite sad that we provide synchronous consultation sessions and hardly anyone attends these synchronous consultation sessions. In other words, the students don't take advantage of the opportunities that are given to them to understand the material better. No? Nagko-conduct ako, for example, ng synchronous consultation sessions. At the start of the semester, I would probably get 5 students, 5 to 10 students attending. After a few weeks, it goes down to about 2 to 3, and it stays that way all the way till the end of the semester. The students, okay, and I hope you're not going to be that way, have a tendency to take the course very lightly. They think they can get away with just taking a look at the slides and taking a look at the recorded sessions. They don't take advantage of the fact that there is an instructor available during the synchronous consultation sessions that can answer their questions. In fact, the students don't even read the textbook. They don't even read the recommended textbook. And that's the reason why we decided, okay, we're going to pilot face-to-face sessions this semester. So are there any questions with regard to that? Any questions? So I hope that's clear. Okay, so let me continue with the course guide. No? Okay, there are going to be. Okay, I'm not going to go through this in detail. No, so UVLE, okay, as you see here, is going to be our course site, and I already showed you the UVLE page that we're going to be using. So this is the venue for which we're going to release all of your course material. Okay. In addition, we're also going to use a forum, a forum site called Piazza. So if you log into Piazza, that's piazza.com, okay, and you'll see this in the course guide, no? You click on this link, you log into Piazza. This is the access code EE 131-2022 S1. Okay. Then you have access now to the forum that is created for EE 131. And what we want you to do, if you have any questions with regard to the course, we want you to post those questions in Piazza. The chances of us seeing your questions are higher if these are posted in Piazza, rather than if you send us the questions individually or through email. No? So the chances are higher. At the same time, your classmates can benefit from the answer to your question. Okay, so I'm just going through the salient points of this course guide. No? Okay, the course is divided into 6 modules. No? 6 modules. Each module will take 2 weeks. Each module will take 2 weeks. And therefore, if all goes well, we will be over. No, we will be over in about 14 weeks, 14 calendar weeks. This is taking into consideration the reading breaks that are provided for by the university. Okay, so if you take a look at the course guide, each module is described somewhat in detail. Module 1, okay, will happen starting yesterday up to the end of next week. And module 1 is really an introduction to semiconductor physics. So this is going to be the most conceptual part of the course. It is an introduction to semiconductor physics. Okay, this is where a lot of students have difficulty because the concepts that are introduced in module 1 are quite abstract. Okay, you're lucky because we already toned down this part of the course. This part of the course used to be much more complicated than what it is now. So module 1 is introduction to semiconductor physics. Okay, and then you have your module 2, which will be on diodes. Well, module 2 actually is a review of basic electronic devices that were taken up in EE 123. So module 2 will be a review of diodes, of your bipolar junction transistor, and of your MOS transistor. And in module 3, okay, we're going to take up also operational amplifiers in a little bit more detail than was taken up in EEE 123. Okay, again, that is 2 weeks. Okay, module 3 now deals with the bipolar junction transistor when used as an amplifier. So you're going to be introduced to the BJT, and you're going to learn how to do both DC and AC analysis of BJT circuits. Okay. After module 3, you're going to have your midterm exam, and that's already scheduled. That's November 7 from 8 to 10 a.m., and that covers modules 1 to 3. Take note that this is going to be a face-to-face exam. So one of the things that we are implementing now in the transition back to normal is we will no longer have synchronous virtual or online exams. It's now all going to be face-to-face exam. Okay, and I think you can guess why we're doing that. We have very bad experience with students taking synchronous online exams, and it's already a matter of honor, honor and the integrity. Okay, so that's after module 3, no. Then module 4. Okay, module 4 will have a reading break in between the 2 weeks of module 4. And this is now the MOS transistor used as an amplifier. No? So you're going to take up DC and transient analysis of the MOS transistor and the different MOS transistor amplifier topologies. Okay. In module 5, okay, this is a more in-depth study of both of amplifiers. More in-depth study of amplifiers, okay? And it is now agnostic whether the amplifier is a BJT or the amplifier is a MOS amplifier. No? You're going to describe amplifiers in terms of their two-port network parameters. So you're going to learn about this. What is your amplifier, whether it be a BJT or a MOS amplifier, can be described or can be modeled by a two-port network, okay, with particular parameters, okay, and you're going to learn how to derive these parameters. Okay. And finally, the last module, which is module 6, and you're going to study the frequency response of amplifiers. So you don't expect amplifiers to be able to amplify all possible signal frequencies, all possible signal frequencies uniformly. Okay. When the frequency becomes too high, then the performance of your amplifier actually starts to deteriorate, and you're going to learn how to determine what frequencies your amplifier can operate without deterioration. Okay, after module 6 will be another face-to-face final exam. So this time it's going to cover modules 1 to 6. So it's a final exam. It's a comprehensive exam. It will cover 1 to 6, but the focus will be on modules 4 to 6. Now, the reason why we say it covers modules 1 to 6 is because the material builds on top of each other. Module 2 builds on top of module 1. No? Module 3 builds on top of module 1 and module 2, and so forth. So it's not possible, for example, to give an exam that's really just modules 4, 5, and 6.
Sir,
Okay,
excuse me po, sir.
Yes, please.
Since hindi pa po approved yung parang F2F classes, parang hindi pa po certified, meron po bang parts po ba dyan sa parang timeline po na parang mag-switch into F2F, or parang yung exams pa lang po yun?
Are you talking about yung face-to-face para sa klasiko? Para
Yes,
sa klase na to? No, for the meantime, we're just going to meet this way, no? Um, um, Actually, ang mangyayari kasi is may official material. I'm going to show you this later, ano? May official material na ipapublish yung handler in charge, because each module has a handler in charge, you know. So there's going to be official material that will be published by the handler in charge, and that's going to be available in UVLE. And you're supposed to refer to this material. And ang magiging face-to-face actually is really just a supplementary lecture. So ang gagawin ko in both my synchronous virtual sessions, which we're having now, and in the face-to-face sessions, I'm just going to be giving supplemental lectures. These are lectures that will supplement the official material, no? Except when it's my module that's being discussed, then the official material and my lecture is probably going to be identical, no? So anyway, no, having said that, so initially habang hindi pa pwedeng mag-conduct ng face-to-face session sa UP, we're just going to have those supplementary lectures this way, no? And then as soon as na-clear na yung facility for face-to-face, I'm going to switch to giving live supplementary lectures. So I'm going to announce that when the time comes.
Okay po, sir. Thank you po.
Okay. So yun, no? So all I already mentioned, all the material will be in UVLE, and this is going to be our grading table. And in the past, our preference is to stick to this table, no? In the past, there have been instances where this was adjusted somewhat, but we had a discussion on this, and we said that most likely we will stick to this table. We will just make sure that the exams we give are reasonable enough so that we get a good distribution of grades. In other words, we get a good normal distribution of grades, which will ensure that the people that study will get good grades, and the people that don't study, will probably not get good grades, ano? Okay, so how are you going to be graded? Okay, there are going to be two bases for your grade. One is the module work that you're going to have to do, which is going to be administered through UVLE. Okay, so this consists of quizzes and of problem sets. So this is going to be administered through UVLE. The quizzes you take online. There's going to be a time limit for the quiz. You take this online. The problem sets are offline, but you have to submit them through UVLE. And for this module work, you can earn up to 20 points per module. So for the 6 modules, that's going to be a maximum of 120 points. Okay? And that is going to form 50% of your grade. 50% of your grade. And then the other 50% of your grade is going to be the average of your midterm and your final exam. And the passing for the course is going to be 60. Okay. Now, if for some reason, and it has to be a very valid reason, you will miss either the midterm or the finals, we will schedule a comprehensive exam. This is after the final exam. And you can use this to make up for your missed exam. But again, it has to be a very valid reason. For example, medical reason. No? We are going to decide collectively, the handlers are going to decide collectively whether your reason is valid or not. So you must provide the necessary documentation to convince us that your reason for missing the exam is really valid. So in that case, you can substitute the missed exam for the comprehensive exam. So these are the handlers of the course. There are 8 sections. Okay. The course coordinator is Dr. Tess De Leon. Okay. And then the other 3 handlers are Mr. Bautista, myself, and Mr. Mindoro. Okay. Are there any questions? Any questions? Yes, si John.
Hello. Hi.
Yes,
Sir, related ito sa pag face-to-face, sir, kasi hindi kasi ako nakapag-prepare like to go to UPD kasi hindi siya na-announce na mag-face-to-face pala dito sa class. So, I don't really know what to do about like going for face-to-face lectures kasi I live far away from UP. And
yeah. Actually, no. I don't know why it was not announced. I think there was a note in CRS that that the class was going to be face to face. Ano? You might have missed it. I don't know.
Ay, yung sa CRS kasi, sir, is ang 131 natin is naka-block section siya kaya walang notice sa ano.
I see. Okay.
Tapos just recently lang siya na specify na face-to-face pala.
Okay. Well, here's the thing, ano. I'm going to check attendance, no. In fact, even this synchronous sessions, I'm going to check attendance. But if you don't attend, because I do understand that sometimes, for example, it's difficult for you to, for example, if online, it's difficult for you to log in. You might have poor internet connection or a poor bandwidth or whatever. If you don't attend, I'm not going to take that against you. In other words, it's not going to be a negative factor in my giving you a grade, no. But when you attend, then I know you're engaged. I know you're engaged. So if I have to make a decision one way or the other, for example, if you're conditional in something, no, and I have to make a decision one way or another, I'm going to take into account your attendance and your participation in the class. No? So if you don't attend, I'm not going to take that against you. Okay. Now the material that I said, the material for this course is going to be published in UVLE. Okay. And all I will be doing in my synchronous sessions, both face-to-face and online, is providing you supplementary lectures, and we will have open discussions. It's a venue for you to ask your questions, but at the same time, the things that I want to stress upon, or the things that I think you should take note of, I will provide supplementary lectures. Okay? Kung tutuusin, you don't have to attend these sessions, no. Yun yung sinasabi ko kanina na my experience is very sad in these supplementary lectures because people usually don't show up, no. Ilan lang yung nagiging suki ko dito sa mga lectures na to, no. People usually don't show up. Okay? That's why we're having the face-to-face. This is to encourage people to take advantage of it, no. But if you don't show up, I guess that's if you're willing to take the chance and just rely on the course material published and taking a look at replays of the lectures, then you're free to do so. No? Does that answer your question, John?
Okay. So hindi pala siya sir, like required or like mandatory na pumunta sa face-to-face?
No. It's in other words, I'm encouraging people to take advantage of the face-to-face sessions, but I'm not going to penalize you if you don't show up. The same way we don't penalize people when they don't show up for the synchronous consultation sessions.
Okay.
But that's your lookout basically.
So no like grade, wala siyang ano sa grades if hindi. Kasi
If ever it's if I, for example, if I give a special exercise, no, during the face-to-face session, if ever I can use that to increase your grade, but never to decrease it.
okay.
No, that's just an example.
Okay. Okay.
Okay. Any other questions?
Sir, follow-up question po doon sa kanina. Kasi di ba po sir magkakaroon po na parang face-to-face exams? Paano po ba yun sir para magkakaroon po ng F2F na exam plus an online exam for those that can't go F2F?
There's no online exam. It's all face-to-face.
So that part is kailangan talaga po.
Yes, no, wala kayong choice doon, ano. We're making it a policy of this course now that the exams are going to be face-to-face exams. Is that going to be a problem for some of you?
Tinanong ko lang po sir for clarification pero at least
Okay.
for
Yeah. No, after all, no, we're supposed to be transitioning back to normal, ano. So I guess that's really part of the transition. The fact that you enrolled in UP Diliman, you should know that sooner or later we're going to have to go back to normal, ano. So you might have enjoyed not having to do so up to now, but you know, at some point, kailangan talaga bumalik sa normal. Any other questions?
Sir, yung sa face-to-face na session, sir, is mabro-broadcast ba yun sa online? Like yung...
We're hoping. We're hoping.
Okay.
That's also one of the things na pinaghahandaan ng EEE. They want to see whether these face-to-face sessions can actually be hybrid sessions.
Okay.
No, a combination of
Yes,
face-to-face and online, but nothing, no commitment yet, ano, because we have to see whether kakayanin ng mga facilities sa EEE.
So clarify lang sir is yung face-to-face sessions, hindi siya like required na pumunta ka talaga or like
highly encouraged.
Yes, we're highly encouraged.
Yeah.
Okay, thank you, sir.
We're providing you this opportunity to...
Yes, sir. Kasi in my case, sir, sa mga December pa ako makakapunta kasi may lab din. So, mukhang makakapunta na ako sa face-to-face niyan. Pero sa ngayong October or November, hindi pa kasi makakapunta kasi ano pa ako ng dorms or things like that.
Yeah. Well, anyway, yeah. Right now, that's yung position namin. Okay. Any other questions before I go to a short lecture just to introduce you to the subject matter?
Hi, sir. Can I just clarify po? And
Yes,
sorry for the clarification po, but to my understanding, there's no set date yet when the first on-site lecture will start po.
Yes, none yet.
If so po, when do you think po is the estimated date when it will start?
Realistically, I think it's going to be October. No, I don't know whether the target of the department is to have something set up before the end of the month. No, but maybe it would be about the earliest would be end of September. More realistically, I think maybe the start of October.
Oh, okay. But if it does, it will be announced naman, right po?
Yes, I'm not going to, hindi ko kayo gugulatin, ano. I'm not going to surprise you, no. We'll give you time to, for example, if you to make preparations, give you time to do that.
Okay. Thank you po.
Okay. Any other questions?
Hello po.
Yes,
Rinig po ba ako?
Yes, you're loud and clear.
Sir, yung face-to-face classes, ay, if ever magkaka-supplementary na face-to-face, same time po ba as our schedule sa CRS?
Okay, that's a good question, ano. I'd like to see. I'd probably poll you, and I'd like to see, more or less how many people are going to really be showing up, ano. Because my two classes are scheduled right after each other. No, I have a 1 to 2:30, and then immediately after this, I have a 2:30 to 4. No, and so it's going to be very inconvenient if I'm going to repeat everything immediately. So I'd like to look, for example, for a common time, and even for these synchronous sessions. No, I'd like to look for a common time that both my classes will be available. So that's one of the things that I was going to ask you. Are you and please, no, maybe you can send me email if it's going to be a problem. If I schedule something, for example, like our synchronous or our face-to-face sessions are going to be, for example, from 2 o'clock to 3:30 every Tuesday, Thursday, something that takes up part your class and part my other class, no. So that's one of the things that I was going to try to arrange, that there be a common time for the face-to-face class. Okay? But that also depends on yun nga, no, on how many people we really get commitment to who will be attending these sessions, kasi we have guidelines, no, like yung separation between students. So kung talagang ma-fill up yung demand of the two classes, I might have to conduct two separate face-to-face sessions.
Sige po, sir.
Nasagot ko
Thank
ba
you.
yung tanong mo?
Yes, sir. Yes, sir. Thank you.
Okay. Okay. Any other question?
Sir, question lang po on yung face-to-face exams.
Mhm.
Since umaga po siya and wala po kasi akong commute lang po kasi yung way ko to UP.
Mhm.
And usually pag masyado po maaga mag-commute or yung commute route ko po kasi is gated by yung times. So baka po malate ako and kung wala pong consideration for that.
uh, let's not discuss that now, ano.
Sige.
Malayo pa yung exam, ano. Normally we don't like people not to take the exams at offset times, ano, because well, sa bagay, if this is going to be face to face, it might be different now, no, but nung pandemic, we didn't want people to take exams offset, no, and I'm sure you know why, no, because of the probability of leakages and stuff like that, no? But let's discuss that when it's near the exam date, and you know your exact situation.
Okay po, sir. Thank you.
Okay, no problem. Sige. Okay, anything else? Okay, so let me just show you, if I can go back to the Ublefe page. Saan na ba siya? Just a while, no? I lost the overlay page just a while. Okay. So again, this is the UVLE page for triple E 13. No, not this. No, ito. This is the UVLE page for triple E 131. Okay, so all the material are going to be organized in these folders. That's module 1 to module 6. The folder for module 1 has already been populated. If I click into this, you're going to see what you have here. You have your study guide. This is the module 1 study guide. So this is going to tell you all about module 1, what the requirements are going to be. Okay. So the objectives. Okay. You have a problem set whose deadline is September 26. The different subtopics. You have video lectures. Okay, video lectures. Links to that at least. No. So this is your module guide. No. So you can see it's been divided into 4 subtopics. No? Semiconductor fundamentals and doping, carrier action, PN junctions, and then BJT fundamentals. Okay, and then you have your you have the slides for module. You have a write-up for module 1A. So you have a very good write-up here, which you can study. The same thing for module 1B, module 1C, and module 1D. And then you also have your slides. Okay, so nakapublish na rito yung material for this week, and soon the material for next week will be published. So please go through this. Okay, so I'm just going to give a very short introduction. Okay. I hope this works. No, nadali. Okay, you can all see my screen. You're all okay with my screen? Okay. Okay, so this is intro to semiconductor physics. Okay. Let's begin with a model of the atom. You would have learned this, I guess, from high school chemistry. In your atom, you have a nucleus. Okay. Your nucleus. Okay. And then around your nucleus, you have what we call shells. So you have shells. So maybe this is one shell. Maybe this is another shell. Okay, so these are your shells. Okay. And your shells are what contain your electrons. So these contain your electrons. An electron will exist in a shell at a specific energy state. No? Now your shells, these are numbered 1, 2, 3, 4, no? And so forth. So those are your shells. And then within your shells, you have what we call orbitals. No? May tinatawag tayong orbitals. And again, no, if you'll probably remember this from chemistry, you have what is called the s orbital, the p orbital, the d orbital, and the f orbital. No? And your s orbital can contain 2 electrons. Your p orbital can contain 6 electrons. Your d orbital can contain 10 electrons, and the f orbital can contain 14 electrons. No? So these are the number of electrons that can be contained. No? Electrons that can be contained. Okay, and not all shells will have all orbitals. No? For example, if you have shell 1 will only have your s orbital. No? Shell 2 will have your s and your p orbital. Shell 3 will have s, p, and d, and shell 4 will have s, p, d, and f. S, P, D, and F. Okay, so what is the significance of these orbitals? These orbitals, yeah, okay, for example, the 2 electrons in the s orbital, that represents 2 quantum states or 2 energy states. I don't want to use very fancy terms, no? 2 energy states that those 2 electrons can exist at. No? The six electrons in the p orbital correspond to 6 energy states, and so forth. No, 10 for the d and 14 for the f. Okay, the most common electronic material is silicon. No? This is the most common electronic material. And the silicon has 14 electrons. That has 14 electrons. Okay, so how many shells will it have? No? Okay, shell 1, you can have 2 electrons. No? This is only s, so this corresponds to 2 electrons. Okay, shell 2, you can have both s and p. Okay, so you have 2 electrons plus 6 electrons, you can have 8 electrons. Okay, now if you take a look at shell 3, okay, so you have, okay, you only have how many electrons left? No? So originally, or silicon has 14 electrons. Dito, 10 na ang nasa shell 1 at shell 2. That means in shell 3, okay, we only have 4 electrons. No? Meaning to say, in your S, meron kang dalawa, and in your P, which can handle 6, meron kang dalawa. No? So this corresponds to 4 electrons. So this is for your total of 14. So ano ibig sabihin nito, no? Shell 3 can have, okay, 8 electrons, no? 8 electrons in the S and P, or in the S and P orbital, but only 4 exist, no? Okay. So that is for silicon. Okay. Are there any questions so far? Any questions so far? Naalala ba nyo to from chemistry? Is this familiar, or is this the first time you're hearing about this? No? Can you just give me a sign that you've heard this before? Okay, so it's not something that is new to most of you. No? Okay. Okay. Now let's consider the silicon atom. Ano? So let's consider the silicon atom. If you consider separate atoms spaced very far apart, okay, this is a picture of what the energy states look like, no, for each of the shells. Ito, no. So this is thinking about silicon atoms that are spaced far apart from each other. Okay, so I already mentioned, no, that the shell 1 has 2, shell 2 has S and P, which is 8, and then shell 3 has only 4. No, even if this P can handle 4 more. No, okay. So these are the energy states. Okay? These are the energy states. Okay, as you make these atoms get closer to each other, okay, so this is your interatomic distance. No? So this is the distance between atoms. So dito, very far from each other. As you make these atoms go closer to each other, what happens? At some point, the energy states in the outermost shell start to merge. And what is the reason for that? The reason for that is because of Pauli's exclusion principle. And you can look this up. Okay. In an electronic system, no two electrons can have exactly the same energy state. Okay. Kung yung mga atoms malayo from each other, that is not considered a system, no? But as they go closer and closer to each other, then they start interacting with each other, no? Habang papalapit yung mga atoms, then there starts to be some interaction between each other. And that's when it starts to form a system, no? And what happens? There's a distance where your energy states start to split into what we call bands. Okay. Now for a certain time, no. Okay, the S and the P will be one continuous band of energies. Okay. But at some point, so what is this point? No? This is the normal distance between your atoms in a solid. So yun yung A, no? The normal distance between atoms in a solid. Okay, if you take a look at the energy level at the outermost shell, it's going to look like this. It's going to look like this. So we're interested in this. No? We're interested in this. Okay, and this is this no. If you expand this is what you call your energy band diagram. Ito yung tinatawag na energy band diagram. Okay. This thing on the left, okay, is an expansion of this red thing. So kinukuha lang natin yung energy profile dito sa A, and we expand it into what you see here in the left, no? And that is called your energy band diagram. Okay. the band formed by the electrons sa baba, that is called your valence band, and the band formed by the electrons sa taas, that is called your conduction band. Now, what is the significance of your valence band and what is the significance of your conduction band? In the conduction band, your electrons actually are free to roam around. They are no longer how do you say it, associated with any particular atom. Whereas in the valence band, your electrons are bound to the atom that they belong to. They are not free to roam around. And it is in the valence band that it is because of the valence band that the solid is actually formed. It is because of the binding in the valence band that the solid is actually formed. Okay, so again, this is your energy band diagram. So we're only taking a look at the energy profile here, in the normal distance between the atoms in a solid. So the top is your conduction band and the bottom is your valence band. Now, depending on the gap, so the distance, this distance, is called your energy gap or your band gap. We call this the forbidden energy gap. Later on, you're going to see why. That's because electrons cannot exist with this energy state. Your electrons can exist up here, down here, but not in the middle. The same thing here. They can exist here, they can exist here, but not in the middle. And that's called your energy gap or your band gap. Depending on the gap, your material will either be an insulator, a semiconductor, or a conductor. So what is the difference between the three? When the band gap is very large, your material is an insulator. Okay, and what is large? Large insulators, typically, the band gap is about 9 electron volts. 9 electron volts. You might say, isn't that very small? Because 1 electron is 1.6 times 10 to the minus 19 coulombs. So this 9 electron volts, you multiply coulombs times voltage. Voltage is joules per coulomb. If you remember triple E 123, volts is joules per coulomb. Your E is coulombs. So electron volts is actually a measure of energy, that is joules. You might say, isn't that a very small amount of energy? Actually, it is not when you consider the distance between atoms in a solid. So if the distance in this forbidden band is about 9 electron volts or greater, then that material is an insulator. Okay. Now why? Because for your electrons to be able to jump to the conduction band, it is going to have to be imparted this much energy. So I said that your electrons here, they're the ones that are responsible for your material being a solid. If you want your electrons to be able to conduct, the electrons here, you're going to have to impart this much energy for it to be promoted to here. So that's your insulator. When the distance is about 1 electron volt, that is your semiconductor. And under normal conditions, maybe under room conditions, okay, this is going to be almost full, but you're going to have a certain number of electrons provided thermal energy. Later on, we'll explain what that is. Thermal energy and energy from the environment that will manage to elevate or to get promoted to the conduction band. Now, in a conductor, okay, the overlap, because here there's an overlap, Dito there's an overlap. The overlap extends to the interatomic distance, So in a conductor, actually, there is no forbidden band. Okay, by the way, no, I show here two quantities, EC and EV. No? What is EC? Let me change color. Okay, EC. Okay, EC is the minimum energy a conducting electron must possess. No? The minimum energy a conducting electron must possess. Okay. The other end, EV is the maximum energy a bound electron can have. Bound, no? Bound meaning to say, yung sinasabi ko kanina, no? If it is bound, that means it is associated with the atom it belongs to. No? If it is unbound or if it's conducting, then it no longer is associated with the atom. It can roam everywhere around the solid. So yun yung EC at saka EV. So in a conductor, okay, the maximum energy a bound electron has actually is higher than the minimum energy a conducting electron must possess. And that's why your valence electrons can actually conduct current. No? Not like an insulator. No? Insulator, because this is very high, then this is always full. There are no empty energy energy levels here. No? In a semiconductor, no, this will almost be full, but there's a certain amount of electrons that will be promoted to the conduction band because of thermal energy. Okay. Any questions so far? So a semiconductor has a resistivity between an insulator and a conductor. It is generally crystalline in structure. What do we mean by crystalline? Crystalline means that the pattern of the position of the atoms is very regular. It is very regular. Although there are non-crystalline semiconductors, no, there are polycrystalline semiconductors. Polycrystalline semiconductors are crystalline in batches. No? So this is crystalline. You see the position of the atoms are very regular. This is polycrystalline, where each of these segments is crystalline. And then this is what you call an amorphous semiconductor, where the arrangement of the atoms in your semiconductor is almost random. So those are the three types of semiconductors. Now, the semiconductors which we're going to cover in this particular course are going to be crystalline. So if you take a look, this is your periodic table of elements. Okay. The semiconductors that are the most commonly used semiconductor is silicon. So it's here. No. Atomic number is 14. That corresponds to the 14. In the older days of semiconductors, germanium was more commonly used than silicon because germanium was more available and easier to process, rather easier to process. No? But nowadays, 99% of all semiconductor devices use silicon. No? So this is what you call your elemental semiconductor. No? Okay. Now, compound semiconductors, if you combine, for example, elements from 3 and from 5 in your periodic table, ito yung compound semiconductor. No? Combination of 3 and 5. No? For example, the one of the most common types of compound semiconductor is a combination of gallium and arsenide. No? So gallium, arsenide, no? This is the most common compound semiconductor. And then you also have alloy semiconductor. Although alloy semiconductor is not that excuse me, is not as common as your elemental or compound semiconductor. So going back to silicon, so we said that we're going to deal mostly with crystalline semiconductor, so silicon. So silicon has a regular pattern of position of your atoms, and that pattern is actually tetrahedral in nature. So this is the base shape. This is the base shape of your silicon crystal. Okay, you have four. The base shape of the crystal consists of four atoms, and that lodges itself in a regular pattern, such as this. No, such as this. It's a tetrahedral pattern. Okay, so each of this, or I think this this would contain 1, 2, 3, 4. Yeah, that's right. No, 4 of these base shapes. No, that's very regular. Okay, you can take a look at this, or you can have a 3D representation of this. No, so this is the 2D. This is the 3D. This is the 3D structure of the silicon crystal. Sorry. Okay, you can have a 2D representation of the silicon crystal. So if I take a look, for example, at this atom, okay, this atom, for example, just do this now. This atom, for example, ang pagmimiyari nito, for example, would be this, and this. No, so you have one silicon atom, and then you have your 4 valence electrons. On the other hand, itong silicon atom naman na to, ang pagmimiyari nito would be this, this, and this, for example. No, okay, and so forth. No, okay. Now, if you take a look at this. Okay, this silicon atom actually has 8 electrons around it. 8 electrons. No? So each silicon atom has 8 electrons surrounding it. No? So that corresponds to 2s2 and 3s2 and 3p6. No? So that is the outermost shell. This corresponds to 8 electrons. So actually buo na yung outermost shell. No? But for its outermost shell to be full, it had to share 4 electrons with 4 other silicon atoms. Kasi ito, ang kanya lang talaga is itong 4 na to, no? Ito yung may-ari niyan. Ito yung may-ari niyan, ano? And so forth, no? Ito yung may-ari, ito yung may-ari. Now, from the point of view of each silicon atom, it thinks that its 8 outermost electrons are complete, no? But actually it had to borrow, or it had to share 4 atoms with 4 other silicon atoms. So that is the nature actually of your covalent bond. That's the nature of the bonds in your valence band. Okay, what happens, for example, if I impart some energy to this particular atom? No? If I impart some energy to this particular atom, so sabi natin, it can jump from the valence band to the conduction band. Pwede siyang tumalon. No? Kapag tumalon siya, butas ngayon to. We call this a hole. You call this a hole, and now here you have a free electron. This free electron is no longer associated with any particular atom. It is free to roam around the solid. And then here we have a hole. Okay. Now, what happens if I apply an electric field? So, kunwari magkaroon ako ng electric field. Let's say this is my electric field. Okay. That is my electric field. What will happen to this electron? This electron will tend to go opposite the direction of the electric field. No? Because it is now a free electron, this electron will tend to go opposite the direction of the electric field. So, will opposite E, no? Your electric field E. Now, what about this hole? It is a hole, no? So the hole itself will not move. But what will happen, It is possible that you have, for example, it is possible that you have this particular atom. No, it is not in the conduction band. It does not have enough energy to go into the conduction band, but it has enough energy to transfer to this hole. So posible itong electron na to pupunta dito sa hole na to. Okay? So this electron, ito, lipat siya rito. And this is now your new hole. So you notice that the free electron here will go opposite E. The hole that used to be here will now end up here. The hole tends to go in the same direction as E. In other words, your hole acts like a positive charge. So that is what happens when you have an electron that is promoted to the conduction band. You end up having two charge carriers. Okay. You have an electron and a hole. Okay, and both of them are capable of contributing to current flow. Okay. Now, if we're talking about pure silicon, you call this an intrinsic semiconductor. At 0 degrees Kelvin, this is at absolute zero temperature, all your covalent bonds are intact. That means you don't have any single conduction electron. This is at absolute zero, and your pure silicon behaves like an insulator. But as you approach room temperature, some of your valence electrons will gain enough thermal energy. This is gaining energy from the environment to break away from its covalent bond and to be promoted to the conduction band. And that is what forms now your electron hole pair. So now you have two ways of conducting current, through your electron and through your hole. Okay. Yeah. This is my last slide. No, this is the last slide that I want to show now. So let's say that N. So let's say we have a solid. N is the number of electrons per cubic centimeter, and P is the number of holes per cubic centimeter. No? Ni is called the intrinsic carrier concentration. That is the number of carriers per cubic centimeter. The number of charge carriers per cubic centimeter. No? And there's a formula. Okay. There's a formula that was derived to compute for Ni. It's a function of the material. It's a function of the band gap. No? This is the energy gap that I was talking about earlier. It's also a function of Boltzmann's constant, which relates temperature to energy in electrons. Okay, and when you compute for Ni at room temperature, Ni is approximately equal to 1 times 10 to the 10 carriers per cubic centimeter. This is room temperature. 300 degrees Kelvin is 27 degrees centigrade. Now note that silicon has about 5 times 10 to the 22 atoms per cubic centimeter. Meaning to say, you only have for every, what is this? For every 10 to the 12 atoms, okay, you only have one carrier. You only have one electron that is promoted to the conduction band. So it's a very, very small number, no? Itong Ni. You have this number of atoms, and only this number at room temperature will be promoted to the conduction band. And if your semiconductor is pure, then N will be equal to P, will be equal to what we call your intrinsic concentration, because the number of electrons will also equal to the number of holes. Now that's a function of temperature. So you see here for silicon at 0 degrees Kelvin or close to 0 degrees Kelvin, your intrinsic concentration is 0, and then as your temperature rises, okay, your intrinsic concentration becomes higher and higher. Room temperature is somewhere here, 300. Okay, your intrinsic concentration is approximately 1 times 10 to the 10, no? Somewhere here. This is your room temperature. Okay, this is for germanium, not commonly used now. This is for gallium arsenide, has a lower intrinsic concentration, and so forth. No? This is gallium phosphate. Okay, so that's the last slide that I want to show for today. No? I think I exceeded the time I thought I would. Are there any questions? No questions? Okay, so that's all for now. So we'll meet again on Thursday at the same time. Okay. So thank you very much for attending our first session.
Sir, quick question po. Where
Yes,
would we, if we want to review this recording, where would we be able to find it?
Yeah, I'll post. What I'll do is I'll post the recording of this session. No, I'll post it in Uble, particularly for our class. And then the slide that I showed, which is actually it's not official. No, these are just some things that I put together for this supplementary lecture. I will also post. No, but remember the official material is already published. You can refer to it.
Okay po, sir. So it would be in the same folder po.
Yeah. I'll
Okay.
do that.
Thank you po, sir.
Maybe not the same folder. No, maybe it will be in. Anyway, I'll create something for our class. No, where you can find it.
Okay, sir. Thank you.
Because I don't want to deluge that folder with too much information. No? Okay. Okay. Thank you.
Thank you, sir. Goodbye.
Yeah,
Thank you.
I'll leave when everybody else leaves, no? Because you might baka may pahabol kayong question. So my practice is to leave when the room is empty.
Sige po, sir. Thank you po, sir.
Thank
Okay.
you,
sir.
Thank you, sir.
Welcome.
Thank you,
sir.
Thank you po. Thank you, sir.
Thank you, sir. See you po sa face-to-face.
Okay.
Hi, sir. Can I just clarify one tiny confusion I have in regards
Okay.
to the silicon atom?
Uh,
At the start, we established that the third atomic shell has the sp and d orbitals.
yeah, but because you only have 14 electrons, no? The D shell will not exist anymore. It will just be the S and the P.
Okay, so we can assume that the D shell doesn't exist, so it's S and P. Oh, because it doesn't fill up the.
Yeah, in other words, the covalent bonds will be among the S and P electrons only.
Okay. And another thing, remember in the 2D representation, right, of the covalent bond when the hole exists, because the current hole will always be filled up by another free electron. Does that mean at in the end, the final hole will be opposite of the electric field? If it assume it all keeps shifting.
The electric field, the action of an electric field is an electric field pushes away positive charges.
Mhm.
Let me go back to that. No, I'll share my screen with you again. No?
Okay, thank you, Bo.
Oops, not that. Sorry. Yeah. Have you taken Physics 72?
Yes, Bo.
Yeah. If you have an electric field this way, no. What does this do? No. If you have a positive charge, the electric field pushes the positive charge. No? So the positive charge tends to go to the right. No.
Mm-hmm.
If you have a negative charge, your negative charge will tend to go to the left. Okay. Okay. Now, if you have, let's say this is a hole, no. Let's say this is a hole. Okay. And then here beside the hole, you have an electron. No. Now this electron is associated with this atom. No? So actually, you have two electrons here. No? These are all electrons. No? Let me do it this way. Sorry. Okay, so this is your silicon. Okay, these are your electrons. Okay, and then here you have another silicon, and let's say you have a hole here. No? Then here you have electrons. So this one is a hole. Okay.
Mm-hmm.
So what will happen if you have an electric field this way?
Oh,
Okay.
it will pull the electrons towards the opposite.
This electron will not have enough energy to go up to the conduction band, no?
Mm-hmm.
Because remember our energy diagram, it's something like this, no? This is your conduction band. This is your valence band, no? This is EC, this is EV. So this electron has an energy here, no? Now it won't have enough energy to go up here, right?
Mm.
But the energy required for it to go here is also within this band. No? So it's
So-
it's possible this electron will transfer to this energy state. No?
Ah.
Well, when
It- oh.
when this electron transfers here, this is now your new hole.
Hmm.
So you think that the hole is moving, no? Actually, it's not really the hole moving, but an electron jumping to occupy a hole. But the net effect is it's like the hole is moving. So for example, next thing we know that this electron now jumps to this, no? And then this is now your position of the hole. And then here, another electron jumps to this, and then this is now the position of the hole. So your hole seems to be moving to the right.
Oh, okay. Yeah, that makes sense. So it's the electron moving in the opposite direction of the electric field as a result of the electric field because
Yes,
it
that's
can't
right.
jump.
No? Yeah, this is for the hole. But this hole was produced when an electron jumped here, no? When an
Jumps.
electron jumped there. So that electron that created this original hole is actually free to move in the solid.
Hmm.
So there are two things now that are contributing to current. You have your electron, this electron that is moving this way, and then you have your hole that is moving to the right.
Hmm.
In other words, every time you have an electron that is promoted to the conduction band, you create what we call an electron hole pair. No, you create two charge carriers. One is the electron and the other is the hole.
Ah, can I ask, is that why electrons flow the way they do in like silicon, for example, or for metals? Or is that different?
No,
Am I thinking of a different concept?
the way electrons flow in metals is the same way this will flow. No, the same way this free electron will flow. This is already promoted here. No, this is the electron that created the original hole. Okay.
Yep.
But
Okay.
but the unique thing in semiconductors is that this hole tends to move also to the right when there's an electric field. That's what's unique in semiconductors. In
Hmm.
in metals, you only have this contributing to current flow, no? The free electrons. You don't have holes contributing to current flow.
Mm. So it adds so I can kind of visualize it like it adds a different variable, and that's what makes semiconductors unique.
Yes, that's right. No, but what makes semiconductors unique is much more than that. You're going to find that out in the succeeding sessions. Anyway, sorry, I have to leave now because I have another
It's okay.
class.
It's okay. But thank you for answering my question, sir.
Okay.
Okay. I'm sorry for taking up your time, but yeah.
No problem. No problem. I don't mind doing this at all.
Okay. Yeah.
Okay.
Thank you, sir. All right, see you next session, Paul.
Okay.
Thank you.